Okay, good morning. Let's get started. So, haven't seen the homework project or the exam on Monday. How was the exam? Okay. Good. We didn't cover too much stuff, but and you got the next homework project, right? The last one, and again a warning: it's not designed to kill you, so don't go overboard. So this time you're actually looking at the actual kernel to see how things work, right? So it's very easy to get lost if you try to figure out every last sentence of what things do, right? So like I say, if something looks like it says log some data structures and go, assume that it's going to log, and I want you to get a sort of a bigger picture, because the more deeper you go, the more likely you're likely to get lost, right? I don't mind if you go deeper to understand how the actual file systems work, but I don't want you to get lost in the process, right? And you'll realize that whatever you did for Fuse is similar to what inside the file system, inside the operating system, things happen, right? You typically have this one data structures where sort of like what you did for the Fuse. You implement some functionality. So you do that for file systems. You do that for paging and all those things. You have an abstract notion of some data structure where your different file system, your different paging module or whatever will implement some of those functions, like what you did for dot get attr equals some function you have, and you have this throughout the kernel, right? And that's how the operating system deals with different file systems. That's how it deals with different scheduling, different what have you, right? So once you understand that kinds of programming, it's a lot of repetitive code for different file systems. If you look at the FAT, and if you look at ext2, ext3, they look all similar but a little different. They look similar in terms of what functionality they implement, but they look different in the exact code that they do, right? And again, start as early as possible. Don't wait till the end. My goal is not to have heavy work towards the end when I'm assuming that you have other course projects and stuff, right? So we're done with the exams and quizzes, right? So we only have the final exam. And if you guys want to move it before the final exam date, that's fine with me. Let me know, or we can have it on the assigned time slot. I forget. Monday? It's fine with me. Take home before the thing, right? Yeah. I can do you can do a take home, or I'll come on that time if you want. You can do it here, kind of thing, right? So at this point, this is sort of the last major topic we need to cover, right? And I want you to start. I mean, we covered almost all the stuff that you would need to do about operating system. We covered the processors, threads, and memory and hard disk and stuff. And now we are trying to put them all together to see what that means. Because real operating systems, these are not as separate as we talked about, right? And you'll notice that the processor scheduling affects your memory stuff, right? So if you swap a new process in, that means a new process has to come. It has to get new buffers and stuff. So they are both linked that way. And all the structures, one of the things you notice is file systems are operating on slow data. So the more buffer you have, the better the performance is. The more buffer means the buffer has to come from somewhere. It comes from the third module, which is the memory stuff, right? So everybody's fighting for memory. Everybody's fighting for resources. So how you balance those things, right? In some sense, operating systems are fairly trivial because you know what the different stuff is. And if you know what the future is, operating systems can do a great job. And the main job is trying to predict what the future would be, right? And they don't know. So all the complexities you see is based on, if they say most Linux users do a certain kinds of stuff, they try to tune it for that particular stuff. That's why the complexity comes in, right? If you knew the future, operating system will be very trivial. It will be very simple because it can do all the scheduling based on what the future is, and they can't do that, right? So I want you to start thinking about that, because whether you like it or not, whether you work in operating system or not, right? Operating system is going to be with you all the time, because one of the things that you notice is anything you do in computer science, your OS is always running and getting in your way. So unless you know how the things work, it'll be hurtful, right? So I saw that Intel is supposed to come up with a quad-core processor for laptops by next year. That either sounds awesome or sounds horrible, right? So what would you think? Would a quad-core processor on your laptop be good or bad? Yeah.
Would not only get like half an hour of battery life.
Oh no, so that's their job, right? Let's assume that they fix that. I mean, I think they do a whole bunch of hardware stuff to fix that, right? I mean, I think the world is moving towards laptops, right? So they're putting a lot of energy into, say, conserving energy and stuff, right? So I think like every extra processor generation, it still uses the same power, right? If you look at the Pentium 4, it used to use 100 watts. The newer dual core uses 30 watts. The quad core uses 30 watts, right? So hopefully that'll be fixed. And I think the newer stuff is the disks are going to go away for laptops, right? Maybe in a year or two, because flash memory is getting cheaper. You can actually get a 64 or gig flash disk for your laptop. Right now, I think it costs like $900, $800, right? But in a couple of years, it'll be $200, $300. And once you replace the hard disk, then you save quite a bit of energy on that one. And another technology that I've seen down the pipeline is one of the major consumers is the backlight, right? Your laptop is not the processor; it's the backlight. So they're going to go with the LED for those, right? So once you do that, it'll become better. Once you cross like 4 or 5 hours of battery life, I think you're good, right? Because if you can fly cross country and still continue to work, then you're kind of good, right? But so assume that hardware is all solved, right? I mean, a couple of years it should be solved, right? Like, so if I asked you 2 years back, would you have a dual core on your laptop? I don't think, or even last year I think it was out, but let's say 2 years back, right? I don't think anybody would have said you will have dual core, right? But you've done the projects, right? So can you imagine what would happen if you have what is the implications for a quad core processor, right? You have to have it all multi-threaded. Yeah, all the applications have to be multi-threaded, which means they all have to worry about synchronization. They all have to worry about those kind of components. And now they're all resource hungry, because there are 4 processors needing memory, right? So you have to have lots of memory, but you have to also be able to feed lots of memory. And all of this can request hard disk things, right? So unless you're increasing a hard disk by 4 times, now everything is going to, I mean, they all want massive amounts of data. So you have to have lots of memory, you have to have lots of this. And so, yeah, the Intel can give you this, quad core processor, put it on the laptop, give you like 5 hours of battery life, right? But unless the programmers and the OS can really use it, it's no use, right? So Intel would really, really love for somebody to come up with a good application where you would want that. And I think the only application you have right now is video editing, burning DVDs or something. Because otherwise you have all this processing, you can't really use it kind of thing, right? So anyway, so that's, I think, down the pipeline. And so we're going to look at disk scheduling and how the disk heads and all move and stuff, right? This is a classic stuff that you're supposed to know, with the caveat that the modern disks are a lot smarter than what we assume here, right? And I'll say what it means in a little bit. For now, let's look at the disk scheduling. So the idea here is, we looked at the disk and we know there's a head, there's a seek and rotation latency and stuff. So depending on, so if you want to request a bunch of stuff, right? If you want to request a bunch of blocks which are spread out throughout the disk, disk scheduling tries to figure out how you should organize them such that you attain the least amount of time between them, right? Think of them as similar to a multi-story building elevator going up and down, right? So how would you run the elevator such that the most number of people can get through the system, right? It's essentially the sort of problem that you solve here. And the hope is if you keep moving a lot of people, then your disk performance goes up rather than if you. So if you, in a multi-story building, if you have, let's say 100 stories, right? If you want to move the person from first floor to 100th floor, then like person from second floor to 99th floor, and you keep going like this, then essentially wasting most of the time seeking or going between the floors. So you would like to schedule them, right? So again, for like the processor, you have to figure out what the accesses are and where the head is. So let's assume that the accesses are for blocks in 98, 183 sectors, a bunch of sectors, and the head is at some point. And if you're trying to figure out how you reorder them such that you get the good performance, right? And again, we assume that this is all being done at the operating system level, right? So the operating system, for this to happen, should know where the head is, right? So the operating system should either ask the hard disk to say, where is your head, and know that, or it knows because it also does the computation, right? It's computing where the head should be at this point. So if it knew where the head is, then it can issue these stuff. So let's assume the OS tells the hard disk, I want sector 98, 183, 37, and so on. You assume the hard disk is actually going to do the way you want it. So assume that the hard disk has no buffer. So anything you say is what the hard disk is going to do, right? And that's where the modern disks differ. But for now, let's look at it like this way, right? So the OS knows where the head is. And the OS knows everything about the hard disk. It knows where the sectors are. It knows where it has to seek and all those things. If you knew that, the simplest seek algorithm is first come, first serve, right? So essentially, you don't do anything. Whatever order you get, you send it off. And you can plot this, trying to see how much you have to seek and how much rotation latency you have to get a sense of what is your expected throughput from the disk and how long the average wait time and so on and so forth, right? So this particular way of drawing the graph basically says, from 53, you asked for 98, so I moved 98, then I moved to 183, moved to 37, and so on. So that means you have to do a certain amount of seek and the rotational latency to get to the actual sectors, right? The other algorithm, so you can think of variants of how you might do that. So the first come, first serve, I don't have to look into the future at all. So essentially, whatever comes in, I just issue to the hard disk. But if I can collect a bunch of them, and if I can use them to predict something, then I can do stuff, right? So for example, if I do a shortest seek time first, SSTF, it's like a shortest job first, right? So from a given head, I sort based on what is the shortest distance I have to go from there, right? So this like some of the processing algorithms we looked at would mean that you move the shortest from where you are, right? Which would tend to keep you in the middle, right? The extremities would be kind of ignored. You tend to be in the middle, right? Because you'll always find something closer to you there. Extremities will get pushed unless you can go to the end, right? So this will give you good performance for people in the middle, or middle sectors. People who are at the edges you may not get to them, right? So it may not be fair, but it'll give you good performance, right? So for example, if you're thinking of, if you take the stuff, if you do a shortest seek first, you reorder them. So essentially, you follow this path, right? And ultimately, you go to 183. But when you are somewhere in the 53 range, if you get another one in that range, you continue to stay where you are, right? Actually, you continue to stay in the neighborhood of where you are. If you get lots and lots of requests which are near you, you continue to stay there. You'll starve the ones which are further away from where you are, right? So it will work if your workload sort of helped you with this stuff. If it will work if what you're doing doesn't interfere with the application, right? Remember so this is all happening at the disk level, not at the file system level, right? So when you did your project, you're issuing certain block reads and block writes and all those things, and all those things are coming here, right? Whatever you're seeing at the disk level has implications something up in the file system, right? So for example, in the file system, in your case, you have to manipulate directories, you have to manipulate the free block thing, you have to get data, right? All of them gets clumped up and comes to the disk. So if you decide to keep serving certain kinds of objects, it may happen that you're actually serving the free block or the directory entry, but you starve the data block, right? So this may give you trouble because your directory entry may be consistent, but the data is not getting to the disk and so on and so forth, right? There are 4 other variants that you look at: the scan and look, and variants of those C-scan and C-look, right? Scan, the idea is, think of it as if you think of it as elevator, it's also called an elevator algorithm. Essentially, it goes from the lower floor to the top floor, right? And then from the top floor, it keeps going down to the lower floor, right? So if you're going up a certain way and your request comes in, then it's served, right? It's more like an elevator. So if you go and press the elevator to the top floor, anybody who comes in and who wants to go in the middle in that direction would get served, right? If they're going in the opposite direction, it doesn't get served, right? In elevator, usually if you get on the first floor, if you get on the 10th floor, and the elevator is going to the 100th floor, right? If you press like first floor or something, it'll wait to go up to the 100th floor, and then it'll go down to the next floor, right? So that's the notion of a scan. But the notion here is it'll always go from the outermost to innermost. So it'll keep going all the way from 1 to 100, and then it'll come from 100 to 1, and so on and so forth. Anything which comes in the way gets scheduled. The others have to wait for the cycle to repeat, right? Yeah.
There's a homework problem on this, and in the homework problem, should we assume that the numbers are increasing initially? Because it doesn't really specify whether which end you're going to initially.
No, I mean, yeah. Initially, you can assume either way, right? I forget what the question was. Does it say where the initial head is?
Yeah.
It tells you what direction.
It tells you what direction it's going.
What?
It does tell you
It
which
tells
direction
you
it's
what
going.
the
Okay.
Okay, if it does, then.
Okay.
Or if it says you're in the first track, right? Then you're kind of stuck with only one direction, right? But in general, these are long-running stuff, right? So you don't worry about those, right? So the scan is you go all the way from bottom to top and then top to bottom. The look variant is you go only up to the level that somebody is actually requesting. So you don't actually go all the way to the top. If there's no request for the top floor, you don't go to the top floor. You just go to the highermost that somebody needs, right? And the C-scan and C-look variants of that is essentially, so if you keep doing this, right? If you keep going all the way to the top and then bottom, the wait time could be higher because it takes twice as much time for you to go back in a certain direction, right? So the C-scan and C-look variants of it would go all the way from the bottom to the top, and then reset back to the bottom floor, right? So it may schedule something, keeps going up, but once it reaches the top, it instantaneously comes down and then starts scheduling, right? And those variants essentially try to give you a little bit more, better waiting time, right? And you can think of this of how you may want in a high-rise building, right? So if you're in a high-rise building and by luck, if it happens that every floor somebody is getting off, right? So if the elevator is going through stopping for everybody and then it's doing the same thing for everybody to get down, that means if the elevator happens to be at this point and you got into the system, right, trying to go up, you have to wait for it to go up all the way and come back all the way to get to you, right? One way to avoid that is to say when it goes up, the only place it goes is to the bottommost floor, and it keeps going up, right? It doesn't quite make sense for elevator because that means if you want to go from here to here, you have to go up, down, and so on. But that you get the idea, right? So that's the scan. Scan goes all the way from top to bottom, even if there's no request. So in this case, it should go from 0. It goes to 0 even though nobody actually requested 0, and then it starts going from there to the higher level. So you basically sort it in that direction, right? And C-scan, when it goes to the topmost, it goes to the bottom. It doesn't take anything else. Yeah.
In the previous picture,
Yeah.
so after it hits 183, it'll go to 199 and then go all the way back to 0.
It'll go to 199 and it'll keep going to back 0. Yeah, if you had a request for, so actually if you don't need to have one request for 199. If you had a request for, let's say, 10, you'll go to 199 and then he'll go back to, yeah. No, it won't go to 0. It'll go to 10.
Oh, okay.
Because in the scan variant, it goes back in the direction. In the C scan, it'll go back to 0 and come back to 10. Yeah, the C scan is the one which does that. Yeah, so C scan, at this point, it goes to 199, even though nobody requested it. And it goes all the way back to 0, even though nobody requested it, and starts coming back from there. Right? And there's nothing magical about this. You're trying to see how you can do all the stuff to get good performance, right? And the C look variant where you don't have to go all the way to the end, you kind of stop a bit before that. And if you do simulations, so it looks trivially different than scan, right? But for certain applications, you going towards the 199 stuff may actually help somebody, right? So for example, in the case here, right, even though if you look at it statically, there's nobody near 199, but if somebody came in at that point where you are at 183, scan may give you better performance because the disk head was moving towards 199 anyway, even though you were not there when the scheduling was done, it can be scheduled on the fly, right? Even though it looks like this is all static, in real disk, these are coming on the fly. So the OS can put you on the schedule quicker, right? So you may win or you may lose depending on how things are. So you've done extensive simulations, you try to figure out how these things work. So if all you're doing is like operating on small files, none of this may really matter. But if you're doing something where you're using the disk a lot, right? So for example, if you're doing a disk backup or if you're playing a video or something, right? Then these things really make a difference because you're doing lots of requests, and good schedule may give you better performance than bad schedule, right?
I was going to say, like, could you show on the last graph how C-look would be different than C-scan?
So in the last graph, C-look from 183, you'll go to 14, right? So it's here, right? There's nothing for 199. So scan would have gone here, and then it goes all the way back to 0, even though there's nothing here. So C-look would have gone here, and from here go to 14, because that's when I think I have a, yeah, so it would have gone that way, right? Again, it looks trivial, but actually if you think about it, the reason is if you are here, right, and, if a millisecond or microsecond after you were here, somebody came in at 184, right? C-look wouldn't have noticed that because C-look would have said you should have gone here, whereas in the scan case, since it was going here anyway, you could have been scheduled, right? So there are some small times when these two are different. Other times they may look the same. So you choose whichever based on what your file system is. And so if you go through the code, right? If you go through the corresponding code, the OS is supposed to figure out how it should scan, right? So if it really was in tune with what your application is trying to do, you may win big, right? But it's not all that trivial because like I said, when you do a file system operation, you're doing disk operation, directory operation, you're doing data operation, you're looking at direct indexes and all those things. So what comes to the disk may not exactly be what you thought it would be, right? So you may win, you may lose, and there's a lot of work done towards that stuff, right? So the reason why I said some of this stuff are in real life lot different, lot more complex than this is, if you looked at most of the hard disks that you buy, right? If you were to purchase a hard disk, one of the specifications they tell you is how much cache it has, right? You might have seen that they have 8 meg or 16 meg of cache. I think it either comes in 2, 8, or 16, right? That means the hard disk has that much of buffer for whatever, right? So the hard disk is actually running a little OS or a little scheduler, little firmware something, right? It has 8 meg of data to play with, right? So that means that even if you say go to sector 1, 2, and 3, what the hard disk does depends on what's in the firmware, right? The firmware can can run another algorithm. So you may be running cscan from your operating system, but the hardware may be running shortest seek time first, right? And the hardware manufacturers don't like to tell you what algorithm they're running, right? Because their point is you shouldn't be knowing this stuff because we know best on where the hard disk is. And one of the things that I think somebody pointed out before is, how do you know where you are, right? The hardware does not want to keep telling you that you are at head position 53. It may have moved you somewhere for whatever reason that you don't have to know, right? Because these things are so complex to manufacture, they may not exactly be going the way you assume in the operating system. So they don't want to tell you where things are. They'll be happy to say, here, give me all the requests, and I'll schedule because I, as the hardware, precisely know what this particular disk is doing. You as operating system don't really know, right? The other reason is we assume that if you think of a hard disk and right, we think of sectors and all those things, we assume that the manufacturing is perfect and everything works, right? You can't do that when you're building a hard disk, when you're selling a hard disk for like 50 or some odd dollars. Right? I mean, it's not possible to make them completely error-free. So what they do is they have some spare sectors, right? So even though they say, let's say that they say the disk is 500 gig, it may actually be able to hold 520 gig, right? So when they manufacture, they do a low-level format, and if they find that this particular set of sectors were no good, they're not actually able to record the contents, they may remap them to something else, right? So they may say, this particular sector should really be here, this particular sector should really be here, and so on, right? So they remap all the stuff. So essentially they have 520 gigs, so they have the 20 gig to do this remapping. They will still give you what they promised you, right? But this disk is a lot different than what you assume, right? So when you say go to sector 1, track 1 or something, right? You assume the track 1, let's say, is here, but this particular hard disk may have this track 0 to be here, right? And when you say I want track 0, 1, 2, and 3, which you assume to be sequential, it may so happen they were all remapped somewhere else, right? So they really don't want you to know that stuff. They really don't want to know where this is mapped. They can also do this dynamically, right? They can also move it while the disk is working. If some sector they find that they cannot, some error, they can remap to something else, right? So all the stuff we see here is purely academic because it really ought to be running on the hard disk, not on your OS, right? And you may remember that one thing we left off was on SAN, right? SAN, I said you have a bunch of, let's say you have 2 hard disks, right? In SAN, we say, I want this hard disk and this hard disk to make it look like a virtual hard disk, right? And that's the nice thing about SAN, because I can create this virtual disk and I can assign physical disk to it and make it work. So if you go to the enterprise anything, you rarely have one disk per stuff. You kind of have these things in a virtual stuff, and we also see RAID, which is one of the ways to do that. So in this case, it's not clear where the sectors are because they are in different disks in different stuff, right? So for the most part, none of these really matter because the disks are so smart. And when you have 16 meg, right, the disk can store so many buffers and do all the stuff. They all should apply within the disk, right? So when you talk to the disk manufacturers, they hate when you talk about this because you are getting in their way of them doing stuff to get better performance, right? Their point is, we know what we're doing, just stick with what you have to do, right? But it's still there. I mean, it's still something that you ought to know. But at the least, it should run within the hard disk on how things do, right? So one of the other things that hard disk manufacturers would really love to go to, the concept to go away is the notion of blocks and sectors, right? They really would love for you to have object-based storage, where you give it a big chunk and they figure out how to organize them, right? The reason is, if you go back to your, I think, physics or math, I don't know which area would have covered it, when it's rotating at certain speed, right? the rotational velocity of this sector is not the same as this sector, right? For a given time, you probably traverse a lot less space here than here, right? So in the assumptions we made, we always say, it's all equal, so you kind of move these things around, which means that you may have to record at a higher density here than here, or you may have to have a lot more sectors here than here, right? From your, I guess it's physics and math kind of stuff, right? So there's all these complications on how things happen. You can't have the same recording density throughout because of the angular velocity, right? So that restricts how much they can put on each sector, right? And that depends on what technology they use, how much they can do. So they really don't like this stuff. They would like for you to say, here's an object, I give you 53 bytes, store it as 53 bytes, don't worry about blocks and stuff, right? And they really push hard. I mean, actually, if you talk to some of the Seagate folks, they really push to have the object-based system. So in fact, most of the firmware, internally, the hard disk treats them as objects, right? When the day comes when you can treat them as objects, they're ready to go kind of stuff, right? So that's something that you should know, because I think somebody pointed out, I mean, these things are extremely complex mechanical electromagnetic devices, and they're doing all this stuff, and they don't want the OS to be making assumptions. All this work made sense when the disks were slow and they didn't have any memory. So if you looked at some disks which are 10 years back, the disks were so expensive, there's no memory in the thing, the disk was fairly dumb. Modern disks are pretty complex, right? And that's why you're able to achieve like 750 gig. It's not like 750 gig means that all your entire disk is entirely perfect. You're doing a whole bunch of remapping inside, which you wouldn't know. So one of the techniques that you may hear about it, you may see in your machine, is this notion of a smart, right? It says .m.a.r.t, which is a standard where the disk tells you its status, right? If you go through one of your operating system stuff, whatever operating system and tools, you can ask the disk what its status is, like how many it had to remap and stuff, and it'll tell you, right? That's a good way to know when your disk is going to crash, because it'll tell you that I'm doing too much of remapping. So from your side, it looks fine, but I had to do too much remapping, right? So it's pretty soon I'm going to run out of remapping space. That means the disk is going to fail, right? So when you get the warning through the smart, you better change your disk, right? Because there's something fundamentally going wrong within the hard disk, right? So last couple of stragglers. One of them is the swap space management. We talked about in the module 3 on memory management and stuff, and we had the notion of a swap. So we were writing stuff onto the disk, right? So it can either be a private swap partition. A lot of systems let you run through a file system, right? I think Windows creates a paging file. Mac can create a paging file and all those things. So if you create a paging file, then if it's like, say, Unix-like systems, then you're going through the inode structure. You're going through the multiple level inode structure for the swap and the corresponding performance stuff, right? So if your swap was going through sequentially, remember the homework project or one of the exams, that was the question, right? If you're going through sequentially on a large file, you get certain performance. If you're going through randomly, then you may have more faults on a large file. So if you're using a large file as a swap within a Unix system, then these two interplay may affect you either positively or negatively, right? And the way they allocate space is also different. So for example, Linux, when you have a new process, right, you create a backing swap space for it right away, even though you need it or not. Whereas on Solaris and all, you only have a swap when you need a swap. So if you have enough memory, you don't get a swap space. So for example, in Linux, so when you start the process, you create sufficient swap space for it, right? So when you need a swap, it's right there. Whereas in a Solaris machine, when you start the process, you may not have swap space. If you run out of swap space when the process is running, what do you think will happen? So if the process needs a new page to store some contents, right? It needs something to be swapped out. But if there's no swap space, you can either leave the page as, you have to leave the process in memory, or you have to kill the process, right? But in the Solaris case, these are servers, so you don't expect to run out of fast space. So this should be okay deal, right? So that brings up to the last concept, which is very important, and we covered a lot more of them in the homework assignment, right? So essentially, the idea came in like early 90s, which is the idea that disks are inexpensive, and how can we put a bunch of these things to get better performance, right? So the notion of RAID is you have multiple redundant array of inexpensive disks, and how can you get better stuff with inexpensive disks? So how can you collect these disks and do something parallel with them, right? And there are lots of levels, and depending on what the level is, you get different benefits and so on and so forth. So let's look at it from the graphical perspective. If you ever go to this web page, I mean, they have a lot cuter pictures than what you have up here, right? So essentially, the RAID 0 is called striping, right? Essentially, which means that if you have 4 disks, you collect all of them into one larger disk, right? So you virtually create a larger disk which includes all 4 of them, right? Which means that, so if you had 10 sectors on each of them, now you have a disk which looks like it has 40 sectors, right? So you can build. So once you have this large disk, you can build a file system which is 4 times what each individual disk can be, right? So this is a nice way to build a larger disk than what you traditionally have, right? So when you have such a thing, you have to worry about reliability, performance, right? Both read and write, and error recovery performance, right? So let's look at the reliability, right? Reliability means that what happens, how reliable is this concept, right? If you assume that each disk fails at rate of p, right? This is simple probability, right? So if you assume each disk fails at rate of p, what would be the failure rate for RAID 0, right? Remember, for RAID 0, the entire disk will fail if any of the disks fails, right? Does it get better or worse? Yeah.
Worse.
Yeah, it gets worse, because if any of them die, the whole system dies, right? So in terms of performance, right? Read performance, do you expect it to be better or worse? Yeah. So it will be better because now you have 4 arms, right? I think one of you asked, why don't you have like a instead of doing a seek, have a like head on each track, right? This is sort of like that. So now you have 4 disk heads. So read and write would be better because now you can write in any one of them independently, right? And error performance does not matter. If one of the disk dies, the whole thing dies, right? If one of the disk dies, then part of your file system is on that disk, and then the whole thing crashes. So this is unreliable, but it gives you good storage, right? So it has its uses for if you understand what the concept is, right? So if you have a desktop and you're using it for something, you can use it for something. So what can you use such a thing for in your own life? What kind of files would you store where you get a lot more storage than what you have, but it's less reliable than what it would have been, right? How many of you use RAID on your desktop, or only one? How many of you know that you have a RAID on your desktop? Many desktops do come with RAID hardware, right? But very few people actually use the RAID concept, right? So what would you store? So what kind of RAID do you have?
Actually, it's RAID 3.
RAID what?
RAID 3.
RAID 3. Wow. Okay.
Yeah, it's weird.
Yeah. RAID 3 is weird. We'll see why it's weird, right? So you use it to store like temporary kind of file, right? You don't really care. You want lots of storage kind of thing. You don't actually store important stuff because it's less reliable, right? And these days, since the disks are so big, so if you have each one of them 500 gigs, so you're getting 2 terabytes worth of storage, right? That's for even 500 gig is so much, so that's not a thing. So the next one is mirrored, right? Which means that everything you write on the main disk is mirrored on the other one, right? So now you have 2 copies of everything. So if you have 8 disks, you essentially only get 4 disk worth of space. Everything you write in one, you have a copy on the other one, right? So what would that do to reliability? Now everything you do, you have another copy, right? And you can use any one of them. So even though we say one is the main, one is a copy, in effect, they're both equal, right? So your reliability would be higher because now you have 2 copies of everything. Even if one disk fails, right? One disk fails, you know that. You can replace the disk while the other system is running. So when it's done, you go through the error recovery, right? Which means that when the other disk comes up, essentially you have to sync all the contents from one disk to the other disk. And once it's done, you're good to go, right? And it's an entirely disk operation. There's no computation. You just copy all the contents from the old disk to the new disk, and then you're good to go, right? And in terms of a read and write performance, how do you think the read would be?
This is fast.
Yeah, you have like 2 copies, so you can go to either one of those, right? So now you have essentially two heads. So in the first case, if there are 2 requests to the same hard disk, you don't get good performance. I mean, you don't get a performance boost. Whereas here, even if they go to the same pair, one can go to the main, one can go to the copy, so you get good performance, right? In terms of write, you make sure that it's finished in one, and then you wait for the write to propagate. You don't have to wait for both the things to be written. So as long as it's written to one, the hardware can make sure that the write will happen in a little bit, right? So you don't suffer the performance benefit. You don't wait for both the copies to be returned. You write it to one disk, and then you move on, and then the other one would be copied pretty soon, right? So the next 3 are barely used, right? Except for, this is the first time I heard someone use that, right? Essentially, they all use the notion of error correction. So if you notice on the mirror disk, you waste so much hard disk. You waste as much hard disk as you have for your main disk, which is wasteful. So what you do is you have parity codes which give you better compression ratio. So for example, one of the things is if you use the memory system kinds of parity, right? The memory system uses parity checks. If you use them, essentially you get the RAID 2, right? Which means that you compute a parity based on the 4 data disks, and you store the parity on the parity disk, right? So one of the simple parity you can think of is the odd parity, even parity thing. So if you do an odd parity check, then you make sure that the parity bit would make the corresponding bits odd, right? You must have seen this from your architecture class. So you store the parity on that disk. So if any one of the disks fail, you can recover by computing the extra data using the parity disk, right? So here you need computation, so you need a computing stuff. So now you need a RAID controller. Unlike for mirroring and stuff where there's nothing really going on, you either have an exact copy. Here you have to do the parity computation, right? And the next 2 variants are you have parity checking, where RAID 3, it's a bitwise parity. So if you think of a block of data, right? The parity is bitwise. So you compute the parity for the first bit of one block and the first bit of one block, which will create the parity for the next block, and you put them in the parity disk, right? Whereas in the RAID 4 case, you take this block, you compute as a blockwise the parity, and that goes in here, right? So it's a little difference in terms of how the parity is computed, but essentially you have a separate parity disk, and if one of them fails, you can get this data back, right? So depending on how strong the parity algorithm that you're using, so now you're having one extra disk, so you're not wasting as many disks, right? But you're adding more computation, right? So if one of the disks fails, you have to do the parity to figure out what the data should have been, and you can keep going, right? So you're compromising on the computational stuff, and you're getting better storage efficiency. So when you buy a RAID controller card, if any of you have priced it out, they usually go for $1,000 or so, because there's a computation going on, right? And so the RAID 5, which is what more common way of storing stuff, it essentially does not have a parity disk, it interleaves it, right? So on the first block, the parity may be stored on disk 1, second block, it may be stored on disk 2, third, disk 3, then disk 4. So these all have significance in terms of error recovery, right? So if you have an error, when you have error recovery, if one of the disks fails and you add a new disk, right, you have to recover what the content is based on the parity, and then you have to write the parity on the new disk, right? So if you have one parity disk, the performance is different than if you have it spread out throughout the disk, right? The other problem is when you do a normal write, right? Now you can't just write to any disk. I have to recompute the parity. So I have to read all the contents from the other disk, right? So if I modify one block which is part of a parity thing, I have to read every other block, recompute the parity, and then write it, right? So in the 2, 3, and 4, since all the parity is going to one disk, that disk is going to be hammered. Whereas in 5, since it's interleaved, right, every write on a block would cause the corresponding parity to be updated. But since the parity is interleaved, all the disks are busy, right? So if you ever looked at a RAID 5 array, the disk will always be active, right? Even if you're operating on one disk, that will force parity on parity calculation and parity writing on other disks. So all the disks would be busy. But the nice thing is, let's say you have one extra parity. So you have 4 disks and 1 parity, and you get good reliability. Not perhaps as good as mirroring in some cases, and it's a lot more compute intensive, right? But you get good performance. And so RAID 5 is typically very popular, but the computation is pretty intensive. So if you do it on your software from the OS level, it'll kill your machine. So that's why you have RAID controller cards, which are very expensive because they actually have to do all this stuff. So if you ever remove one of the disks and put it back, right, you'll go through 4 or 5 hours of rebuilding because every block it has to read from all the other disks, do this computation, and store the parity, and so on, right? And there are variants. So RAID 6 has 2 parities. So it's like RAID 5, but it has 2 different algorithms. So it computes parity using 2 different algorithms and interleaves the parity with the disk, right?
Why isn't there 2 P's in every disk though for RAID 6?
It's one of them is Q and one of them is P, right? It looks like it's all 2 P's, right? Yeah, there should have been P and Q on every disk.
Oh, okay.
Yeah, and they don't have a Q at all, right?
Oh.
And there are combinations, right? So one of the combinations is RAID 0 plus 1 or 1 plus 0, where RAID 0 plus 1 is essentially you stripe. So if you have 8 disks, you stripe 4 disks and you stripe 4 disks, and then you mirror both of them. And RAID 1 plus 0 is you stripe this way and then you create the mirror, right? And they have different performance and different characteristics. So these are also common. So if you buy desktops, they typically tend to come with RAID 0 or 1 or variants because there's no parity computation, right? It's inefficient, but for a desktop it's okay, right? This is a cheap way of you having a backup because, like, if you do a mirroring, everything you have there's extra copy, right? And I'm really surprised that not many laptops come with mirroring on, right? Because laptops you expect the hard disk to fail, and this is a good way to do that. But I guess there's not enough space, right? But if there's something that I would like, this is one of those things because if one of the hard disks dies in a laptop, your data is completely gone. Now if you have a mirroring, you have another copy, right? So that pretty much wraps the stuff. So when you're doing these writes and all those things, you have to make sure that things go into the hard disk. When you have lots of this buffering either from the OS and stuff, we are doing this disk scheduling and stuff, which kind of delays the stuff, which means that if a power goes off, it may not actually have gone to the hard disk. And that's something that you need to worry about when you're building a database. If you're building a database or something, you want stuff to be committed. You want stuff to go all the way to the hard disk. But all the things we said here was, for performance, we delay what write goes in. We kind of, we make certain stuff to delay where it goes, and that has implications on how you implement stable storage. And you need to worry about those when you're worrying about databases and stuff. So database class has to worry about when I say write, I mean write, right? And OS says, okay, you said right, but I have to do it when I feel it's right. And then this says, oh, I know you said right, but I'll do it when it has to do because of performance. And how do you balance those is a concern. Right? So we'll wrap up we'll look into the protection security and then go on to tying everything together next week.